Let's write a program now to generate a sequence of integers, and for each, check if it's prime as a way of demonstrating how to write functions and how to think about the code. So recall that a positive integer greater than or equal to 2 is prime if it's only divisible by 1 in itself. So given n, if it's evenly divisible by anything in the range of 2 to n minus 1, then it's not prime, which allows us then to write a program to easily check to see if a number is prime. Because given n, we just check for each of these numbers. And if any of these divides evenly into the number, then it's not prime. But if I make it through all of these numbers and none divides evenly into n, then it's by definition prime. Now this isn't the most computationally efficient way, but it's a way that's easy to understand. So how are we going to do this? Well, I'm going to write this function, and let's say I call it is prime. And it's going to be given a number n, and we know n has to be an integer, int n. And if the number n is prime, then we need our function to tell me that it's prime in some way. So how do we do that? Well, some languages contain variables of type Boolean. Now, if you're talking about in the general sense, it's capitalized. Within a particular programming language, it might not be capitalized, but it is named after somebody, so it is technically correct for what I'm talking about here. So let's say we have some language that has a type called Boolean. And so we have a variable x. Well, what that means is we could do something like this, say Boolean x equals true, or Boolean x equals false. Booleans take on true or false values. Now C89 doesn't have Booleans. C99 introduced Booleans in some form, but C89 doesn't have them. So is there any way we can do something equivalent to this, where we could return a true value or a false value? Well, remember when we talked about conditionals and the idea passed on to loops as well, but we said that when we're writing the test condition, say when we're writing this, if x greater than 5, this ultimately has to reduce to something with a truthfulness value. And we said that if this is false, it will be represented as 0. And if it's true, it will be represented by some non-zero number. And as we saw, it was 1 when we were writing it like this. But if I simply just wrote in there if 17, that would be considered true. So this is a way to represent truthfulness. So what I'm going to do in my function is that if it finds out n is not prime, return 0. If not prime, and if prime, return 1. I could use negative 99 if I wanted, or 17.6 or something like that. I wouldn't want to use 17.6 or even negative 99. The problem with 17.6 is I'm going to make the return type int. So I can't use 17.6. Negative 99 would technically work, but the convention is to use 0 and 1 to represent false and true. So that's what I'm going to do as well. So let's write some code to see that in action. So we said int is prime, int n is our function declaration. We'll go ahead and copy this down here. Int I, and we said to determine if the number is prime or not, we need to check the integers from 2 to n minus 1. So for I equal 2, I less than n, which would be n minus 1. Is the last number we check, I plus plus. And for each of these, I want to basically ask a question. If n mod I is 0, which means I divides evenly into n, if that's true, then the number's not prime. So I'm going to return 0 right here. And typically then I'd include a comment probably to say false. Because there's other situations where I might use false for something else, or not true, or however I'm doing it, right? At what point do we know that the number is prime? Well, a mistake to make here would be this. So what's the problem with that? Well, the problem is, let's say that we pass in 5, which happens to be prime. But what it's going to do is it's going to say, well, does 2 divide evenly into 5? No. So it's going to come down here to return 1, which is going to come back and tell us, yes, 5 is prime. But I never checked 3 and 4. Which also means, now in that case we got lucky and it was the right answer, but let's say we pass in 9. 2 doesn't divide evenly in 9, but 9 is not prime. So we don't want to, on the very first number, which is 2, check and say either it divides by 2 or not. All this really does is tell if this number is even or not. It's not telling us if it's prime or not. So we don't want that. And instead we have this. So what is the loop? That's the entire loop. Remember, we said that if I don't use curly brackets to represent the body of my loop, I can do exactly one thing. Well, that one thing here is this. Now you may look at it and say, well, isn't that really 2 things? Well, no, because these are a package. You can't write if something and just leave it at that. Now I can write if something semicolon technically, but then you're saying don't do anything if it's true. But this is still considered one thing in terms of how the language works. So I think, unless I made a mistake, that's our entire function. So now let's check some integers. So let's go up to 20. And for each of them, I'm going to ask the question, is the number prime? If. Now you may be tempted to write this, and this will be fine, is prime equal 1. When we print the numbers prime. That's fine in terms of legalities. But actually I prefer something else. So let's think about how this works. Well, if I pass in 7, we'll eventually get down to return 1. It'll say if 1 is equal to 1, then print 7 is prime. That's fine. But actually I prefer this from a readability perspective, because I wrote my function name to be a verb. And so, at least to me, the way I'm reading this is, if I is prime, then print that it's prime. It's about readability. I could do the other, it would be fine, and there are times when I'm more explicit where I say, check that this really is true or whatever. But here I'm okay with this. So let's see if I have my code worked out. 2, 3, 5, 7, that looks correct. Let's try something else. I don't spot anything that's not prime, so I think that's correct. So this is really all it took to do this. Now let's talk about performance. Does this work? Sure. Now when they're trying to find the next largest prime number, I'm pretty sure they don't do this because it's too computationally inefficient. So let's see a way to improve it. So let's think about this. So let's say I have a number like 100. So you know the factors of 100, because this isn't prime, are 1 and 100, 2 and 50, 4 and 25, 5 and 20, and 2 and 10. I think I found all the divisors of 100, right? So what's the midpoint? And I'm putting it in quotes to indicate it's not the way you normally think about it. What's the midpoint of this in the square root sense? What's this right here, right? The midpoint, if you say what's the midpoint, well, 50 would be the midpoint. But what I'm getting at is that For divisors of any particular number, they have to have one that's less than the square root and one that's greater than the square root, unless it's, say, 1 itself. These come in pairs. These go together, these go together, these go together, these go together, right? So we have like 1, 3, 9. That's the midpoint. 1, 2, 4, 8. Square root of 8 then has to be in here. Okay, 2 point something. So what's the point of all this? Well, if I'm checking these numbers right here, and I don't find anything that divides evenly into 100, assuming that was a prime number, well, then I'm not going to find anything over here because they come in pairs. All right, so I don't know the square root of any prime numbers since they're not integers. But let's say we said, looking at the code, I see 37 is prime. So we have 1 and 37. Somewhere in here has to be the square root of 37. If any other numbers in here are multiples of 37, they have to be paired up with something over here. So I don't really need to check past the square root, is what I'm getting at. That will save us some work. Another way to make your program more efficient would be to realize that you could check to see if they're asking if 2 is prime and say, yes, 2 is prime. Then after that, only generate the numbers from 3 to n minus 1 in multiples of 2. So only check the odd numbers because 2 is the only even prime number. So let's write another function. And this also is another nice benefit of functions. If you didn't know what a function is, I would take all this code right here, and this would be in the body. And then if I said, well, let's test out another algorithm, your choices are either modify code that works, which then may be difficult for you to go back and get to work correctly again if it turns out your suggested changes don't really work, or cut and paste the code and put it somewhere else. So I am going to cut and paste code, but I'm going to do this. So this prime 2. But now I'm going to do this. I'm going to say is prime 2. And we know this works. And let's put is prime 2 here. So I'm going to need the math library. And now we keep going as long as we're less than or equal to square root of n. So why do we say equal? Let's take 9 for example. 9 is evenly divisible by 1, 3, and 9. Well, we're not going to check for 1, and we're not going to check for 9, so we need to check for 3. But if I say as long as I is less than the square root, all I would check is 2 and conclude that 9 was prime. So I think that's really the only change I need to make. So I still need to check for the square root of 9. Whoops. So like before, we talked about the power function. I need to manually link in the math library, which I've done with -lm. Run it. And I think these are the same values. So that works. But how much effort did it take to get there? Well, let's see how much. So 97 is prime. Let's do this. And so we know 97 is prime, so let's call our two functions, because once again, because I'm using functions, I can just put in the function name and easily do something. And I'm going to do something else while I'm here. Int count equals 0. And now I will need the curly brackets. So for each number I check, I'm going to increment my counter. Actually, let's do this. I don't actually need the curly brackets. Let's demonstrate something else. I do need my count variable. So what am I doing? Well, the way the loop works, whether I have curly brackets or not, when it gets to the bottom of the loop and it returns up here to do the increment, it will do everything in this portion of the for statement. So it's going to increment I and also increment count. And so then what I can do is come down here and print how many times count worked. Because what I want to see is, well, how much effort am I actually saving by doing this? So there's the two counts. Let's see what happens. So when I was checking for 97, we didn't check for 1 or 97, which meant I had to check the other 95 numbers in that range. For the second one, since I stopped at the square root of 97, whatever that is, I only had to do 8 iterations of loop. So that's an order of magnitude difference. And this is for a small number. You know, what would be, I don't know, really large primes. Let's say you just want to check 1001. I don't know if that's prime or not. Oops. Did I break something? Oh, did I break something? Sorry, now I have a debugging problem because I don't figure out what I just did. 1001. Oh, it's probably not prime. So I hit the return. That's what happens when you make these things up on the fly. Let's go back to the old version. Let's find a large prime. 997. And this is the second version of the function. So let's compare it to the original version now, since we know 997 is prime. 995 versus 30. So 30 times 30 would be 900. So it's still a pretty big difference in terms of effort. So I like readability, but when it doesn't hurt readability and it doesn't take a lot of extra effort, performance is a nice thing to have as well. So there's an application of using functions, and we'll add more applications of functions in the videos that will come later as we add more language elements and can do more in a particular function.